Assalamu alaikum kids. So this right here is a series of videos in which we will discuss your 2024 AS level physics course. Okay. Let's start off with the very first topic, which is base and derived fundamental quantities and their units. All right. So first of all, let's discuss what physical quantities are. So physical quantity is anything that can be measured. A physical quantity is usually made up of two things, which is your magnitude and your unit. So let's say, for example, you have this 10-meter measurement in front of you. The 10 in this measurement is the magnitude, while m meters is the unit. All right. So I hope that made sense to everyone. This right here is pretty basic stuff that you probably have done in your O levels as well. Acha. Now, moving on, another important part of physical quantities is to be able to estimate them. All right. So we are going to talk about estimation in much more detail later. But right now, what you need to be able to know is that you should be able to take a reasonable estimate of values such as the mass of a person. All right. So the mass of a person could be somewhere around 80 kilograms. So there are certain estimate values that you'd want to remember. All right. So again, that's what you need to know about physical quantities. Now we broadly divide our physical quantities into two categories. One is fundamental quantities and the other is derived quantities. Let's take a look at fundamental quantities first. There's 6 fundamental quantities in front of you. These fundamental quantities have SI units. Both the quantities and their units you need to remember. All right, so that's very important. So the very first fundamental quantity is length, and length has SI units meters. All right, then you have mass, which has SI units kilograms. You have time, which has SI units seconds. You have temperature, SI units Kelvin. You have current, SI units ampere. And then you have amount of substance. Now, amount of substance is more used in chemistry, so we're not going to discuss much of that, but you still need to remember it. So amount of substance, again, the SI unit is moles. Now, these right here are your fundamental quantities, and all the derived quantities are basically a combination of these fundamental quantities. All right, so let's take an example of force. Now, force is mass times acceleration. Now, mass is a fundamental quantity. Acceleration is a derived quantity. Why? Because it's a combination of length and time. All right. So if you take a look at the units of mass, mass is just simply kilograms. But acceleration is meters per second squared. Now, meters, of course, is the base unit or the SI unit of length. And second squared is time. So basically acceleration is a derived unit whose base units or fundamental units, again, you can call them either one. So their base units are in terms of meters and seconds, which are the fundamental quantities, length and time. So let's take a look at force. Force is mass times acceleration. The base unit of mass is kilogram. The base unit of acceleration is meters per second squared. And together they form the base unit of force, which is kilogram meters per second squared. Now, kilogram meters per second squared is not the SI unit. There's base units, which are combinations of the fundamental quantities. And then there is the derived unit, which we just simply call it the SI unit. All right. And the SI unit of force is newtons. So fairly simple. You've got SI unit. Again, could be newtons for force, joules for energy, watt for power. All right, they aren't in terms of their base quantities, so they aren't in terms of the fundamental quantities, fundamental or base quantities, whatever you want to call it. But then you may have force as kilograms meters per second squared. Now this right here is in terms of your fundamental or base quantities, hence we call it the base units. All right, so SI unit, you need to remember. Base unit, you should be able to derive it. All right, and we are going to go through that in much more detail. Now, in physics, as far as your derived quantities are concerned, all of those derived quantities have to be a homogeneous equation, all right, or need to have their own homogeneous equation. Now, every physical quantity in physics is homogeneous, all right, which is, again, you can derive the same quantity from various different formulas, and they should be able to give you the exact same formula every time. All right, so let's say, for example, you have energy. Energy is half mv squared when we are talking about it as kinetic energy, or it's mgh if it's potential energy, or it's just force into distance if we are talking about work done. All right, but they are all measured in joules, which has the base units kilogram meter squared per second squared. All right, so I hope that this right here so far is making sense. Again, I'm going to repeat. So you have fundamental quantities, you have derived quantities. Derived quantities have SI units and base units. SI units are just given according to the name. So force is newtons, energy, joules, so on and so forth. But then there are base units for the same derived quantities, which are the units derived from their fundamental quantities. All right, so you should be able to tell. So force was a relatively simple one. Let's discuss the base units of several other derived quantities. So first one we have is pressure. Now what's pressure? Pressure is force upon area. That's the formula. So the very first thing you need to be able to do when you are deriving the base units of a derived quantity is you need to know the formula. All right. Now, again, like I said, SI unit and then base units are different. So SI unit for pressure is, you should be able to tell from your O-level scores, it's pascals. All right. And then you have pressure. So force upon area. Force is mass times acceleration. And area is, again, area is meter squared. So I know the form, I know the units directly. So I'm just going to write area over here. And then we can say that, okay, mass is what? What's mass? Mass is kilograms. The unit for mass is kilogram. The unit for acceleration is meters per second squared. And then the unit for area is meters squared. Now, another important part of being able to derive base quantity, base units is that you do not want any negative powers. So you have seconds, which has a negative power 2. So I'm going to remove that. I'm going to say kilograms meters over meter squared second squared. Now the meters and the square is going to cancel, and you're left with kilograms per meter second squared, or you can just write it as kilograms per meter per second squared. Now writing it with negative powers towards the end is fine, but as when you are deriving the base unit, it's really not a good idea because it's just going to complicate things more. So the SI unit is pascals, while the base unit is kilogram per meter per second squared. All right, I hope that made sense. Then you've got energy. So energy using mass, mgh. So mass times acceleration due to gravity times height. So mgh is gonna be, so I know the units of each of these quantities. Mass is kilograms, g meters per second squared. So I'm just going to write it as meters upon second squared, and then height is again meters. So now you've got kilograms meter squared per second squared. Now the base unit is kilogram meter squared per second squared. You can either write it in fractions or you can write it in exponents with a negative power. Or the SI unit, on the other hand, is what? That's joules. So I hope that made sense. Energy. So we then have energy using half mv squared. Okay, so any constant is generally, any constant is ignored when deriving a base quantity. So I'm going to ignore the half, and then I just have m and then v squared. M is mass, so that's kilograms. V is velocity, so that's meters per second, but that's squared, so I'm going to square it. Now the exponent outside the bracket is distributive, so I'm going to square the meters and I'm going to square the seconds. So you've got kilograms meter squared over second squared, which is the same as what we have here. So again, different equation, but still giving the same base units. All right. Then you've got power. Now, again, you need to be able to, you need to know the formula. And so the formula for power is energy over time. Now, when you are doing power on its own, of course, you'll have to derive the units for energy as well. But I already know that energy is kilogram meter squared plus per second squared. So I'm going to just use that, kilogram meter squared per second squared divided by what? Divided by time, which is seconds. Again, I don't want negative power, so I'm going to bring the second down, second squared down. So kilograms, and then you've got meter squared, and then you've got second from this time right here, and then you've got the second squared from here. So now the base unit for power is going to be kilograms meter squared per second cubed, which can also be written as kilogram meter squared per second cubed. And the SI unit for power, everyone knows, is watts. So the base unit kilogram meter squared per second cubed, and the SI unit is going to be watts. Then you've got charge. Now we know that charge is current multiplied by time. So charge is current multiplied by time, which is current. The base quantity current has the base unit. The fundamental quantity current has the base unit amperes. So I'm just going to write A, and time is seconds. So amperes, seconds is the base unit of charge. Again, we call it coulombs. All right, the SI unit is coulombs, while the base unit is amperes, seconds. Then you've got potential difference. Now, potential difference is an interesting one. So let's talk about the formulas you have for potential difference. One is V is equals to IR, but I'm not going to use it. I'm not going to use V is equals to IR. Why? Because again, R itself has a complicated set of units. So being able to derive R's units is going to be a little problematic. So instead, I'm going to derive V, the potential difference, from a formula you learned back in O-levels. V, the potential difference, is equals to energy or work done per unit charge. All right. So I hope that everyone remembers this formula. Very first thing that you do in current electricity back in your O-levels. So energy. All right. Again, we already have the base units for energy, which is kilogram meter squared plus second squared. So I'm going to write it as such in fractions. Okay. All right. Then you have charge. And what's charge? Again, we just found out what charge was. That's amperes seconds. All right. So now you have the base unit of potential difference, which is kilogram meter squared per what? Per amperes second cubed. And together, what's the SI unit of potential difference? That's volts. All right. So I hope that all of this made sense to everyone. So being able to derive the base units is almost a guaranteed first question in your AS level physics paper 2. All right. And then you have several questions in P1 as well regarding the derivation of base units. All right. So again, a very important part of your course. So I hope that all of this made sense to everyone. Inshallah, that's it for today. And I'm going to see you in the next one. Bars out.